All right, so yesterday we finished up talking about the halogenation reaction with bromine. The reaction we're going to start with today is a variant of that reaction, and it's called the Halohydrin reaction. So let's take a look at what happens in the Halohydrin reaction. We still start with a basic alkene. However, instead of using just bromine, we use bromine mixed with water. So what do you think the first step's likely going to be based on our experience yesterday? Yeah, nucleophilic attack of our double bond, and we know that bromine's a decent enough electrophile because it's very polarizable. So just like before, we can show this using two arrows if we want to. We can show this bromonium ion product. And in this case, we've got Br minus floating around. That was our leaving group. And we've got water floating around. So I'll draw it as OH2. And if we don't have water around, the only nucleophile we have is bromide. Bromide will attack in and ring open it. But in the halohydrin reaction, water is a good nucleophile too. And that can actually outcompete the bromide. So water in this case will attack in, just like we saw yesterday. That will result in a product that is protonated. So I'm going to draw these two methyl groups sticking up. And then on this side, we've got two methyl groups sticking down. What do you think the last step's probably going to be? Yeah, just deprotonation. Usually this reaction is done with an excess of water. So water is a decent enough base to just reach over, grab a proton, and give us our final product. Okay, so if we look at this addition reaction, is it syn or anti-addition? Anti-addition. So the bromine is added onto the opposite face of that alcohol, so this would be referred to as anti-addition. And specifically, we would refer to this as a beta halo alcohol, meaning that the halogen is coming off a carbon one away from the alcohol site. Some of you have noticed on the website I put a bunch of flashcards. If that helps you to study, go for it, print them off. You can use them as just study aids. If it helps you to make flashcards, I would encourage you to do that. Sometimes the process of writing out these flashcards can help a lot instead of just printing them. The key feature with this reaction is that water outcompetes the bromide as a nucleophile. So it's really just a variant on the same halogenation reaction we saw yesterday. So let's take a look at the stereochemistry of this reaction, which is a little bit tricky. I'll show you guys an example. Sorry, let me rephrase this. Regiochemistry. I'm messing up your notes. The regiochemistry is a little bit unusual, and it's something we have to pay close attention to because it's going to show up again and again in a lot of these reactions. So let's say we've got this alkene, where we have one side of the alkene that's more substituted than the other. The first reaction, we're still going to form the bromonium ion. So let's show those arrows. And we'll kick off the bromine. Let me clean this up a little bit. That looks a little bit better. There we go. We've got our bromonium ion. And now we have to consider the water attacking in, right? So let's consider two options. I've got one option going this way, another option going that way. And I'll do this first option with blue. And in this reaction, we're going to have the lone pair on the oxygen attack the carbon on the right. So it's going to attack in right here and slingshot this open. Instead of drawing the final product, let's take a look at the intermediate. Or sorry, the transition state. Where water is starting to form a covalent bond here. And when we do this, it's important to remember that bromine's now got a partial positive and oxygen's got a partial positive down here. And let's compare this to the transition state if it were to attack the other side. So I'll do this one in green. And we'll slingshot this open using a green pathway. And just like before, this bromine's carrying a partial positive, and same thing with this oxygen, so we'll indicate that. Which pathway do you think is more likely to occur and why? And I want you guys to talk about this with your neighbor. This is an easily confusing concept to get through, so try to really argue it through. Don't just accept something as fact. I'll give you some things to consider too. So usually when chemists are looking at these reactions, they'll look at steric effects and electronic effects. So sterically, you could ask yourself which side is more easily accessible, or you could say electronically, which one is more stable. You could argue both ways with this one. There's not necessarily one right answer in terms of the way you argue.
It was a transition state.
All right, so let's talk about this as a class, you guys. Let's consider sterics as being the driving force for this reaction. Sterically, which pathway is more accessible, the blue pathway or the green pathway? Blue pathway. So sterically, we'd say the blue pathway might be more likely due to sterics. What about electronically? Which one's going to be more favorable, the green pathway or the blue pathway? Green pathway. Why is that?
hyperconjugation?
Yeah, it's interesting. So if we think about this green pathway, this carbon, the one going through that making and breaking of bonds, has more hyperconjugation. That's going to stabilize it a lot more than this carbon over here that only has one carbon attached to it. So experimental evidence shows that this electronic pathway is actually the driving force for this reaction, and this will be the more stable transition state. This is something that confused the heck out of me when I took organic chemistry. I was like, well, how can you anticipate whether or not it's sterics or electronics? The reality is you have to run the experiment, see what the outcome is of that experiment, and then after the fact explain why it happened. It doesn't make intuitive sense, but it's really how chemistry is done. You can disprove a reaction mechanism, but it's really hard to prove a reaction mechanism before you carry something out, right? So in this case, this one is not likely, which means that the alcohol in this case is always going to add in to the more substituted side of your alkene. So let's go ahead and just draw our final product from this. And then last but not least, we're going to show that deprotonation event. So I'll do minus H plus down here. And we're going to form our alcohol. But our alcohol is always going to come off the more substituted side. So let's even make a note of that. I'm going to write it down here. Your OH will always come off of the more substituted side. Due to electronics. Meaning that transition state that we just saw is much more stable when it's coming off of the more substituted alkene. Does that make sense? It's still anti-addition, but we also have to consider which side the alcohol is coming off of. It's still going to be anti, though. Are there any questions with the halohydrin reaction? Yep.
Yesterday you had said that with chloride, it doesn't work out very well. This is kind of more related to the Horn reaction. So in the Horn chloride does use chloride and it reacts the same way as bromide. So are we going to...
Are you talking about with halogenation reactions?
Yeah.
So with halogenation reactions, 90% of the time you see a halogenation with Br2. Maybe 10% of the time you see it with Cl2. Br2 is much more polarizable because they're big, bulky molecules with huge electron clouds. It will work with chlorine. However, chlorine's a really tough reagent to handle because it's a gas, which makes it somewhat impractical in a lab setting. And it's really, really good at oxidizing things too, so you just don't see it used as often as bromine. Yeah.
At the start, why does the double bond do a nucleophilic attack against the bromine instead of a water, where water has a permanent hydrogen bonded dipole moment, whereas the bromine just has the temporary one?
Okay, so that's a good question. You were saying up here, why did the pi bond attack bromine as opposed to taking a proton from water? In this case, water is just simply not acidic enough to protonate that pi bond. The reaction that will win out is that nucleophilic attack of bromine. The only time you protonate a pi bond is when you have a really, really strong acid, such as HCl, HBr, or HI. So you typically only observe that with halo acids.
I have a question before we move on.
Yeah.
At the top in the center, I've been curious about this. Right now, all the groups on the bottom, right and left, are methyl groups.
Mm-hmm.
So it doesn't matter which one you choose to be a wedge or a dash.
Exactly.
But when we're getting, say that the starting material had an ethyl going up in the top left and then, I don't know, terbutyl or something random coming out the bottom right, how would you choose which, like when it's in that triangle formation, how do you choose which to make a wedge and which to make a dash for your final product?
That's a good question. So Grace was asking, how do we know which ones to make dashes and wedges? Let's take a look at an example problem. We'll just do one real quick. So let's say we've got this compound, right? We've got an alkene. It's a tri-substituted alkene. And we're going to react this with bromine and water, our halohydrin reaction. And we know in the first step, this pi bond's going to attack, the bromine's going to get kicked off, and we're going to form this three-membered ring in all of these situations, right? In this case, can you guys see how this ethyl group right here and this methyl group are cis to one another on the alkene? They're on the same side, so to speak. That means that they're both going to be dashes or they're both going to be wedges in this intermediate. So for example, in this one, I'll draw the ethyl group on the left as a dash, which means this methyl group over here, must also be a dash. And then this methyl group right here in green must also be a dash here. A wedge. Holy cow. So it's important to make sure that you think of this alkene as kind of laying on its side when it's doing that nucleophilic attack. So another way of thinking about this is let's draw our alkene like this, like that. And actually, let me even show these pi bonds kind of like this. When you've got bromine that's getting added in, this pi bond can attack from either face and kick off that bromide, but the stereochemistry remains the same on each of those carbons. Does that make sense? Mm-hmm. And then let's just do a little bit of practice. Which carbon is the water going to add into? Yeah, the more substituted one. The other important thing to consider too is we could have an enantiomer for this one. So I'll write plus En. So we could have two different intermediates, kind of like we saw yesterday with that halogenation reaction. However, in each intermediate, the water is going to add into the more substituted side and slingshot this open. The resulting product is going to be anti. However, this methyl group is going to stay as a dash. The ethyl group is going to stay as a dash, and then this methyl group is going to stay as a wedge. So try to keep that stereochemistry the same as you proceed through the reaction mechanism.
For the enantiomer, is the ethyl group would be a wedge?
Yeah, with the enantiomer, you could draw out the enantiomer of the intermediate or just write plus En. I'm fine with you doing it either way. Does that make sense?
Yeah.
These require a fair amount of practice to get good at, and it takes a little bit of time before you get comfortable with it. So try to do as many practice problems tonight and tomorrow as possible. All right, so let's continue on. We're going to do some cool chemistry. The first reaction we're going to look at is called anti-dihydroxylation. We're going to use some alphabet soup to accomplish this. So let's say we've got an alkene, and we're going to treat it with a molecule called MCPBA. And then in step 2, we're going to treat this with acid and water. Instead of adding in one alcohol, this reaction will actually add in 2 alcohols. However, as you can probably tell by the name, the alcohols are going to be anti to one another. So you'll end up with 2 different products. And what's the relationship between these? Yeah, they're enantiomers, right? They're non-superimposable mirror images of one another. So in this case, you get a racemic mixture. However, it's going to be anti-addition for both of the products that you get out. So now the question is, what the heck is MCPBA? MCPBA is short for meta-chloro peroxy benzoic acid. Right? It just rolls off the tongue. It's the best way to win at Scrabble. Throw this down on the board.
Is it boarding to dig enough?
I don't think you could make this using Scrabble. So let's draw out what this looks like. We're actually going to use this reagent a few times during the year. So a peroxy group is anytime you have an oxygen-oxygen single bond. So you can see we've got a peroxy group right here. However, it looks kind of like a carboxylic acid with one extra oxygen, so it's a peroxy acid. And then the chlorine in this case is going to be in this position, which is referred to as a meta-substituted benzene. And we'll go over how to name benzenes when we reach that chapter. But this is MCPBA. And this is a really commonly used reagent anytime you want to accomplish anti-dihydroxylation. Yep.
Is that an O at the end, or that's?
Sorry, this should be an oxygen. Yeah. The good thing for you guys is I'm going to just briefly go through the mechanism. We're not going to go through all the nitty-gritty details. I know sometimes it feels like I'm not trying to make things simple, but I really am, I promise you. So in step 1, we're going to treat this with MCPBA. And when you do this, you're going to form a cool functional group that we're going to spend a lot of time talking about later. This is referred to as an epoxide. What sort of functional group is an epoxide? It's an oxygen between two carbons.
What are those?
It's an ether. So it's a 3-membered ring with oxygen, so it's a fancy ether. Does it look like a very happy ether? No, it is a very, very unhappy ether. The thing I will tell you guys is you don't need to know this mechanism. It's shown in your book. However, I found that students just get super overwhelmed when I ask them to draw out the entire mechanism. So I want you guys to primarily focus on the fact that you can convert an alkene to an epoxide using MCPBA. All right, so in the next step, step 2, we're going to treat this with acid and water. Fastest reaction in chemistry is going to be acid-base chemistry, right? So in this case, the oxygen is going to grab a proton. Now this looks pretty similar to a couple of the reactions we've seen already, right? With the bromonium ion, we saw a 3-membered ring where one of the portions of the ring had a positive charge. This time it's got an oxygen with a positive charge. Okay, water is floating around. We know water can act as a nucleophile. So it's going to do similar chemistry to what we've seen before. It's going to attack and then ring open this. Actually, let me draw out the hydrogens here. However, it's important to note that it can't attack from the top face, right? Because that epoxide's already kind of coming out of the page at us. The water can't approach from that face because it's too sterically blocked. It's actually got to attack from the backside. So let's make a note of that. This is really similar to the anti-addition that we saw with the halohydrin reaction in the halogenation. And in this case, it could attack from either side, so we could get two different products out. So I'll just write plus En for our enantiomer. And then what do you think the last step's going to be?
Deprotonation.
Yeah, deprotonation.
Always.
So don't forget your proton transfer at the very end. And there we go. We've made our own diol out of this. It's important to remember that it's going to be anti-addition 100% of the time with this reaction. However, you do need to account for possible stereoisomers. So quite often with these reactions, you get enantiomers or diastereomers out of it. The cool thing is that this reaction is kind of our intro to our chapter on ethers, and we're going to talk about this a lot more, I think, in chapter 12 or 13, but it's a good introduction. All right, guys ready for another reaction?
You insist.
Only 2 more today, I promise.
Yeah, that was great.
You guys didn't know how good you had it last time. All right, the next reaction, instead of anti-dihydroxylation, we're going to do syn-dihydroxylation, right? So we'll do the same example as before. So we'll use our cyclohexene. However, this time we want our alcohols to be on the same side. Is there an enantiomer? Why not?
Internal play.
That's a meso compound, right? So if we tried to draw the enantiomer, we'd just be drawing the same molecule twice. You could draw the same molecule 1,000 times for all I care. It doesn't mean it's anymore, right? So the question is, how can we get the alcohols to add to the same face instead of the opposite face? And in order to do this, we've got a couple of different options. The first one is osmium tetroxide, so OSO4. I know my S sometimes looks like a 5, so that's OSO4. And then for your second step, you're going to use sodium bisulfite, so NaHSO3, and water. I've honestly never done this reaction. The main reason being that osmium tetroxide will make you go blind if you get it in your eyes. It is super nasty stuff to work with. Does anybody know why it causes you to go blind?
Retinol?
So yeah, you're right. In your eye, you've got all these rods and cones as your photoreceptors, right? All of those rods and cones have double bonds in them. If you get osmium tetroxide in your eye, it's going to react with the double bonds in your eyes. It's super nasty stuff to work with. People tend to avoid this reaction because it's kind of gross. But it shows up on the ACS exam, and I like to show it to you guys.
So we're going to do this reaction after mercury.
Yeah, so vision, I'm not going to go off on a tangent, but like vision, it works by those bonds, rotate and go back and forth. So if they stay as tristis-trans, they just get stuck there, basically.
In fact, it'll form an organometallic complex with osmium and get stuck there. Yeah, it's really nasty stuff. So you don't need to know this mechanism. But you do need to know the chemical transformation because this does pop up on the ACS exam. That's my one complaint with the ACS exam is they show reactions that were common in like the 1950s, but nobody does them anymore. There's a better way of accomplishing this reaction that still gives you a syn diol. However, this one's also pretty nasty. This one you would use potassium permanganate, so KMnO4, sodium hydroxide. However, you have to be very, very careful with this reaction. You have to run it very cold. Potassium permanganate is kind of like firing a cannonball at this molecule. If you increase the temperature too much, it'll do a bunch of other chemistry too. So you have to keep it super duper cold to stop it at the diol. If you heat it up, it will actually oxidize it past the alcohol and form things like carboxylic acids.
Is this one in 2 steps as well, like the other one?
No, this one's actually a one-pot reaction. Yeah, the first one is a 2-step reaction where you form an organometallic intermediate and then reduce it off. For this one, you can do it all in 1 step. So for both of these reactions, you don't need to know the mechanism, but they are useful for synthesis problems.
So we just need to know the reagents. And
Just know the reagents and the final product.
Okay.
Yeah. All right, so we're building up our toolbox. We've got one more reaction today. This reaction is actually kind of neat. So I'm going to draw this a little bit oblong. We've got our cyclohexene that we had before. And this reaction, we're going to treat it with ozone, so O3. And then in step 2, what we're going to do is treat it with something called DMS. Or, if you don't want to use DMS because it's stinky, you can use zinc and water. So let's make a little note of what DMS is. DMS is dimethyl sulfide. This stuff reeks, and essentially it's just sulfur in between two methyl groups. But it's really nice at doing simple reductions. So DMS is a somewhat common reagent that you might see in your textbook. Zinc and water obviously doesn't stink very much, so most chemists prefer to use it. I like to think of ozonolysis as a molecular scissor for double bonds. So if we're going to cut these double bonds, I just draw a red dashed line, and I'm going to even draw in the hydrogens that are coming off of this double bond. And really all we're going to do is insert an oxygen. So I'm going to draw it like that just to indicate that we've inserted two oxygens where that double bond used to be, but let's draw it in a little bit better way. Come on. Ugh, this does not like my hand today. So 1, 2, 3, 4, 5, 6. These are the exact same molecule, right? So it's a 6-carbon chain with what functional groups on the end? Oh, come on, guys. Aldehydes, right? So this reaction can be used to actually convert an alkene to an aldehyde, which is a cool transformation. The other thing, too, is what if we replace those hydrogens with an alkyl group? What would we be forming instead of an aldehyde? A ketone, right? So this reaction can be used to form aldehydes or ketones. I think I was talking to Alan about this the other day. You guys have probably seen this reaction without knowing about it. How many of you guys have gotten on your childhood bike after a few years and noticed that the tires are all cracked? Or an old car that's maybe been sitting out in the sun? You guys see that rubber cracking? That's actually an ozonolysis reaction. We've got a trace amount of ozone in our atmosphere that will actually break down the double bonds in rubber and cause that cracking to occur. So this is a pretty common reaction, but it's also a useful organic transformation. If any of you guys, I don't know if anybody here was around for the Challenger mission, but what happened in the Challenger mission? Does anybody know why the Challenger shuttle exploded?
It was too cold, and the rings that were supposed to seal part of the rocket weren't sealing anything, and it caused an explosion in the rocket.
Yeah, exactly. With the Challenger mission, one of the takeaways from that was that there were these rubber gaskets that were meant to hold parts of the rockets together. However, they had deteriorated primarily due to an ozonolysis reaction. When you've got a rocket going near the speed of sound or faster than the speed of sound through our atmosphere, it's being exposed to a lot of ozone, and they should have replaced it. So this is a very practical reaction. All right, let's take a look at a few examples. And I want you guys to help me predict what the products would be out of this. So step 1, we're going to treat this with ozone. Step 2, I like using zinc and water. What product will we get? So let's try to figure this out and then check with your neighbor. You don't need to show the mechanism, just anticipate what the products would be.
Yeah. What's it out?
Then give me a thumbs up if you think you got it. A few people. So first step, we pull out our pretend scissors, right? We cut that double bond. So when we do this, we've got an oxygen inserted on both sides, right? What's the relationship between these products? They're identical, right? And this is an example where we are actually forming a ketone instead of an aldehyde because we've got a tetrasubstituted alkene. You guys want to do some more practice? All right, let's do a few more. Yep. We'll get to that. So if we look at these, what's the longest carbon chain for those ketones? 4 carbon, so it's a butane. Specifically, the suffix for ketones is an ONE, so an one, like acetone. So this would be 2-butanone for each of the products that you get out. We'll cover that way later, though, so don't worry about naming ketones yet.
If there was 9, would it be no.
Yep, no. All right, let's do ozonolysis with this one. I'm going to kind of extend this double bond, make it bigger. There we go.
No, there's carbon though.
Oh, carbon, sorry.
How many of you guys think you got this one already? A couple people? One of the products is pretty easy to spot. The other one's a little tricky. So we'll pull out our molecular scissors. We're going to cut it, right? So we've got an oxygen like that. What's our other product look like?
And O bond to carbon.
Yeah, if we think about it, right, we had 2 hydrogens added on here. I'm just going to redraw it over here to give us more room. Does anybody know the name of this molecule?
Carbon monoxide.
Not quite.
See, let's just
That's
see.
triple bond.
Carbon monoxide CO. This is formaldehyde. How many of you guys are in the anatomy class with the cadavers? A few people might have got a slight whiff of formaldehyde.
Not yet.
They're actually trying to get it out of use for cadaver labs. Does anybody know why?
It stinks.
Yeah, it stinks. It can cause you to pass out. Another practical thing is it's been linked with cancer. So they're trying to find suitable replacements for embalming fluid to get away from formaldehyde. So in this case, you get an aldehyde, a small molecule aldehyde, and you get a ketone. All right, do you guys want one more challenge one?
Sure.
All right.
Give it to us anyway, yes.
Why don't they make you wear gas masks when they do that then?
The reality is nowadays they don't use very much formaldehyde in the cadavers, and you guys are working under big hoods anyways. So this is a bicyclic ring system, so you guys remember that from last term, where an alkene is a part of one of the rings. Like what?
Molecular scissors?
These are kind of like that. There was actually a big debate a couple years ago about mechanically pulling apart bonds, and everybody kind of scratched their head at that because it seemed bizarre. But it got into all these high-level journals and was even in the news. Then it came out later that his grad student made up all of her work. It was really embarrassing. Needless to say, he does not work in the U.S. anymore.
So which country hired him?
It was a big embarrassment for the chemistry community.
What school was it?
UT Austin. All right, how many of you guys think you got this one? A couple people? Give me a thumbs down if you're absolutely stuck and you have no idea even where to begin. A couple thumbs downs. It's the same concept as before, right? We're going to cut that double bond. Are we going to be making aldehydes or ketones? Yeah, I'd say aldehydes, right? We've got hydrogens coming off here and here. So if we insert an oxygen into each side of that double bond, or what used to be a double bond, we'd be making two different aldehydes. And in this case, we still have this ring over here, right? This ring wasn't cut, so we've got a 5-membered ring. And on one position, we've got an aldehyde, and then 2 carbons over, we've got another aldehyde. And in this case, both aldehydes would have to be coming off the same side of the ring, so we could draw them both as dashes. Are we going to be making any enantiomers here? No. So in this case, it's a meso compound. You only get one product. So this is kind of a novel use of ozonolysis. All right, we have a couple more minutes left. If you guys want to just take a quick look at your pod and start working on it, you're welcome to do that, and I'll hang out in the room for a couple of minutes.
What's all those double arrow rate in
Double arrows where?
the pod? It's not equilibrium arrows.
It just means synthesis, so it may take more than one step on the pod to accomplish the transformation.